Good day, everyone. This afternoon, we're going to talk about stability. And what we're doing is using the behavior of the systems in the Laplace domain to enable us to determine if a system is stable or not without necessarily having to do the complicated mathematics. You remember we discussed that one of the things about transforms is that you're able to go from one world or one universe where the deliberations are fairly complicated into another one where we can use simple mathematical manipulations and get some idea of what the system is doing in that domain, and it will give us an idea of what it really would do when we come back to time. Now, remember again from early on, we try to deal in this course with fairly predictable systems. So we're looking for systems that are bounded input and bounded output. What we mean here is that if I put in an input to the system that occupies some range of values that is bounded, so it will not go outside of those range or of that range of values, that the output of the system likewise will not go beyond whatever the system boundaries are supposed to be. And a system is stable if when I put in a bounded input, I get a bounded output. And we are assuming for most of our purposes here that we are dealing with single input, single output systems. There are systems where you have multiple inputs and multiple outputs, and you will meet those later on in some of courses like your controls courses as well. But for our purposes here, we are specifically dealing with single input, single output systems. We also know from some previous discussions that if you are given a system that has a Laplace transform of the form here, once you can factorize it and you get it into these complex numbers, into this the partial fractions or complex numbers, you get it into the partial fraction form, that you would get a solution that in this case is composed of two decaying exponents. So once you're dealing with roots here that have s plus something, that is going to translate when you take the inverse Laplace transform into e to the minus something, which is a decaying exponent, which means that eventually whatever input is put into the system, it will die out as time goes forward. And what we also saw previously, and you could go back to lecture 8 to check that if the poles are located, and remember the poles are the roots of the denominator of the transfer function, if the poles are located in the left half of the S-plane, remember we draw the S-plane as a real part and an imaginary part. All right, I could just put here real and imaginary. If the poles, when we draw the S-plane, are located in the left-hand side of the S-plane, then the system is stable. And in fact, the unnecessary and sufficient condition, which is a terminology that you will meet also in things like your controls, that a necessary and sufficient condition for stability of a system is that all of the poles of the system must have negative real parts. So if even the poles are complex, so let's say for argument's sake, the poles for the system is 2 plus or minus j, right? That if the pole itself had minus 2 plus or minus j, once it didn't really matter too much about this, but once this part was negative, that would be sufficient for the system to be stable. In other words, whatever you got, remember the inverse Laplace of something with a complex, what do you call it, a complex root would give you a e to the minus a something, and and together with this would give you either a cosine or a sine, right? So the combination of those would give you decaying sines or decaying cosines in the actual answer, which eventually, I mean, a decaying sine or a decaying cosine will eventually die down, right? So the system is stable, it just oscillates. Right, and in fact, if you plot the poles on this one, you will see that the poles for that particular one has real part. The real part is -1, but the imaginary part, so it is -1 plus or minus 2j. All right. Simple poles are just the terminology. Simple poles are poles that only occur once somewhere in the S-plane, right? You have things like double poles where on the particular spot you would have like repeated poles or double poles, and those are to distinguish from the single poles, which means that at one location you only have a single pole occurring. So it's fairly easy to find if I give you a 2 or 3 pole system without too much of difficulties. You can solve the equation, you can factorize the denominator, and you can get the poles and determine if the poles have negative real parts or not. But what about a question like what is down below, which is an old past paper question, but is the sort of thing that you can encounter, right? So you have a feedback system, and you want to find, of course, the closed loop transfer function of it, and then the range of values of a variable k that will drive this system unstable. So of course, the approach we can take, and we know already from part 1, or we can answer part 1 of the question fairly easy already. We know this is G and H. So we have done this enough already, and you know that the transfer function of this whole, if you were to simplify that, will be G over 1 plus GH. And you substitute for G and you substitute for H, and then you would get the whole transfer function in terms of S and K. Then, so where do we go from there? The problem now is to find the values of K that will make the system unstable. So in other words, as we go through here, if I were to find the poles are going to be S equal to K plus or minus something, right? Might be some complex variable or something, but S is going to depend on the value of K. And if K turns out to be negative, it is fine. The system will be stable. If K turns out to be positive, it means that the real parts of the poles are going to go across now into the right-hand side of the S-plane, which will make the system unstable. And those are the values of K that the problem is asking to solve. Now, it is possible to do it the hard way, which is to, after you've solved G over 1 plus GH, to look at the roots of the numerator, the denominator polynomial, sorry, and get the poles and try to solve it, which may or may not be possible easily, and then see what value, how the answer varies according to K. In fact, in controls, when you go to do controls, there's a technique called the root locus technique that you're going to learn, which does exactly that. As you vary K, you watch the S-plane and you see how the poles move. They'll move in particular paths and so on. And if the path does something like this, then, you know, this side, the negative half of the S-plane is all right, but this part here is unstable, okay? But that is the longhand approach to it, and you have to do that for particular types of systems. But here, if you just want a general idea, is this system stable or not, without having to do fancy mathematics and without having to do the root locus technique, what we're doing today is to look at a technique that is available to us and that will allow us to quickly get an answer as to if the system is stable or not. And it is similar to the other sort of techniques that we've used, like the final value theorem that can see what happens to the system in a steady state, the initial value system, theorem that can tell you what happens to the system when it now starts up. Okay, so again, this is another tool in the arsenal that we have. So if you look at the stability of the system, what the method that we're going to use is something called the Routh-Hurwitz stability criterion. Routh or Ruth but I think the pronunciation, as I've heard over the years, is Routh. Okay, so the Routh-Hurwitz stability criterion. And it is a fairly straightforward tabulation method. It's kind of like working with determinants, but it's very straightforward. And the hardest part is to make sure that you get the table set up correctly, because after that, it is pure algebra. There's no calculus in it. There's no differentiation, no inverse transforms or anything of this sort, which is why I'm doing the lecture like this on the other part of it, because it's something that is fairly easy for you to listen to the lecture and understand, and then we'll come back in class and actually do some problems on it. So here's how it works. So step one, you need to find something called a characteristic equation of a transfer function. The characteristic equation of the transfer function. And the characteristic equation basically is the denominator of the transfer function. You set that equal to 0, and you have what is known as a characteristic equation of the transfer function. In other words, you're trying to find the characteristic equation is really where you find the roots of the transfer function from. So if I take 1 plus gh and I put that equal to 0, that is my characteristic equation. And what you would normally do is to solve for the roots of that, because the roots of that would be the determining factor on whether the system turned out to be stable or not. Normally, when you simplify the characteristic equation and we express it in a descending polynomial in S, so after you've done all your hard work and you get it into this form, you put it into the form S. You start off with the highest order of S and you go right down to the constant, right? Whatever the constant is, and you let that equal to 0. So for instance, here's a characteristic equation here. We don't know where that came from, but whatever it is S4, s to the power 4, plus 2s cubed, plus 3s squared, plus 4s plus 5. That would have been, this is a 1 plus gh for whatever that transfer function happened to be. And the issue now is to figure out what are the poles of that, or what is the behavior of the poles, without necessarily having to find out what is the pole to try to solve that. So step 2 now. So step 1 was to get it into a particular form, like we have there in yellow, descending orders of S. The next thing is to tabulate it now in a form. So we draw a table and you use paper. This is one of those things like the block diagrams where you use some paper. So what we're going to do now is to set up a table, right? And the first thing we do is you look at the characteristic equation, and the first row of the table, you put the highest order of S in it, right? So in this case, it's S to the 4. And then the remaining row, the remaining elements of that row, you start with a coefficient of S4 in this case, or whatever the highest order was. Then you skip 2, then you put in the next coefficient, then you skip 2 and you put in the next coefficient until you run out. So in this case, S to the 4 was the highest order, so I am going to put in the coefficient of S4, which is 1. Skip 1, I'm going to push in the coefficient of S squared, which is 3. Skip 1 again, I'm going to put in the constant, which is 5, right? So whatever n is, the coefficient is an, then n minus 2, n minus 4, n minus 6, and so you go on. The next row now, we put in the next coefficient, the next order of S that occurs. In this case, so S4, S3. Eventually, what we're trying to do is to get a table with S squared, S to the power 1, and S to the power 0, right? That is the eventual outcome of the technique. So we finish the S4 row. The next one now is the S cubed row, and we put the coefficient of S cubed, which is 2. We skip, we put the coefficient of S, which is 4. We skip, and there's no other coefficient left, right? So we put a 0 here, right? So 0 is a placeholder, so you put the 0, leave it blank. Fair enough? So, and this table tells you the numbers there, tell you the number of the coefficient. So once you do that, if you have the table set up, so we've already set up this row and this row. We now have to complete the remaining rows. And this is the theory behind this is something called, in polynomial theory, is something called Sturm's theorem, which we're not doing. It's a mathematical technique to manipulate polynomials. We are not interested in how it on how to derive the theory, but interested in how it works. So the next step down, remember we had S4 here, and we have S cubed here. The next row that we have to fill in is S squared, the coefficients of what would be that row. And how we do it is according to the little formula here. And I'll just draw it out because it's fairly easy. It's just a graphical thing. To get Bn minus 1, Bn minus 1 is the next missing one. Remember, we have the first two rows already. If you go back here and just clear up this a little bit, we already have these two rows filled in, right? The first two rows. So we now want to fill in what is the S squared row here going on. So if I go down here now, so this is going to be my S squared row here. The first entry in the S squared row is an minus 1 multiplied by an minus 2 here, which is this. And you take away an multiplied by an minus 3. That's this. And you divide by an minus 1. Okay? So it's a cross multiplication. It's a little bit. So step 1, let me put it in a different color here. An minus 1. So you find that product. Yeah? Then you take away this product and you divide by the where you started. So you're starting everywhere. You're starting everything from here. So you multiply 1, you take away this product, and then you divide by whatever the first answer was there. Yeah? This is actually, it's the reverse, or it's like a flip of a when you were evaluating a determinant. You remember in a determinant, you go the other way, right? In our case, we're starting with this one, subtracting this one, and then dividing it by the first value there. If you do that, so in this case, and then of course, we go back, sorry, let me backtrack here. So that gives us the first entry here. The second entry now, which is going to be Bn minus 3. For Bn minus 3, we start again with the same, everybody is always going to start with these two numbers here, and then we use the next two. Remember, for Bn minus 1, we used these. For Bn minus 3 now, we're going to use the same first row and the third row now. So again, it's going to be this multiplied by this minus this multiplied by this, again divided by that. Right? And if we check here now, and if necessary, this one now, if necessary, this one would have been this and this row here. So it would have been something, if there was something existing here, it would have been this by this, multiply minus this by this, divided over that. And you keep going until you have nothing, until these columns, you're getting zeros on top. All right? So if you do that carefully, you should get the two answers that I have here. And we could double check that fairly quickly. Right? The number here is supposed to be 2 by 3, which is this by this, minus 1 by 4, which is 4, all over 2. 6 minus 4 is 2 over 2, which is 1. So that part is correct. And then we can check the other one here. This one here is supposed to be 2 by 5, which is 10, minus 1 by 0, which is 0, over 2, which is 5. Yeah? So we have that there. And as you would imagine now, we continue down and we just keep repeating that process, filling up the space. So this one here now, this missing one, is going to be 1 by 4, which is 4, minus 2 by 5, which is 10, over 1, which is minus 6. Yeah? And this one here is going to be 1 by 5, which is 5, yeah, minus 1 by 0, which is 0, over 1. So 1 by 5 minus 1 by 0 over 1. So I should get 5 inside of there. And you keep doing that until the table is complete. Yeah? And if you do that now, then the next step down is to look at this column here. And this is where the actual work of the stability criterion comes in that, first off, a system is stable if all of the elements of the first column, so you go back here, this is the first column that I've circled here, all of the elements of the first column have to be strictly positive. That is, that they have to be more than 0. So that's step one. So for a system to be stable, it will only be stable if all of the elements of the first column are strictly positive. And the second part of the that we can get out of this is that the number of roots with positive real parts is equal to the number of sign changes in the first column of the array. So remember, the system to be stable, everybody has to be positive. If there's some negative number in the first column like we have here, then the number of sign changes is going to tell us how many of the poles of that system has real parts that are positive, which mean unstable. So if you look at this thing, how many sign changes do I have? Now you have to go down column by column to see what the sign changes look like. So you go down, sorry, row by row. So from here to here, there's no sign change. From here to here, there's no sign change. From here to here, there's one sign change because it's going from minus 1 to, sorry, it's going from 1 to minus 6. And then from here to here, it's going from minus 6 back to plus 5. So that's another sign change. So all in all, we have 2 sign changes. So this characteristic equation that we had before, the one with s to the power 4, etc. Let me just pull it up here. This equation here has at least two roots that have positive real components in them, and that is why the system is unstable. The system, of course, is we know it's unstable because we have a negative number in that first column, and the criteria say that everybody in this column is supposed to be positive. So this table is 1 is not stable, and then 2, there are 2 roots because there are 2 sign changes inside of here. So there are 2 roots in that characteristic equation that have positive real parts. And in fact, if you were to go into MATLAB and solve this, or use some other technique, because there are complex roots all the way through, so it's not something that is particularly easy to factorize. If you do that, you're going to see that there are two roots here, which is the 0.29 plus or minus J1.42. Right? Well, we're not concerned about the J1.42 part, because that will give us the exponential thing, but the plus 0.29 part is the thing that is going to give it an issue. And if you see on the axis, the S-plane here, this is the S-plane, right? This is the main S-plane axis here. You notice that, let me draw that a little bit better. All right. So we have the S-plane here, and we have, so that is, those are the two axes of this, the S-plane here. You notice that this pole and this pole have positive real parts. So in other words, if I were to find the inverse transform of that, because it's a complex, I'm going to get probably an increasing, what do you call it, an exponential, an increasing exponential sinusoid. So the answer for this equation, well, probably those two roots will give you something like that. It will keep increasing in amplitude as time goes on until it reaches the limit of the system. Remember, we started off by saying we need bounded input, bounded output. This is not bounded output. The bounds of that will keep getting bigger and bigger as you go along. All right? So that is part one of the stability discussion. Listen to it carefully. It's fairly straightforward, but there are a couple of situations that we have to do that we have to be aware of, and that is what we'll take a look at in the second lecture on this. Okay.